Good morning, everyone. It's time to get started. We have a couple of sections to look at today. Hopefully we can get into 3.8 as much as possible. Since we're a little behind, I'm hoping we can get caught up before spring break. If not, I'll have to give you a video to watch over spring break, which I know is nobody's idea of fun. So we're going to be taking a look today at derivatives of inverse functions. We're primarily looking at the derivatives of inverse functions formula because we need it in order to develop the derivative of the inverse trig functions. So that's primarily where it comes into play. We don't use it so often other than that because it's really actually more work than just finding the derivative directly, but it does help us find the derivative of the inverse trig functions. So what we're looking at today is a picture right here of a function f of x, which is here in dark blue, kind of starting on the y-axis and extending upwards. And then we have the graph of its inverse function, which is over here, starting on the x-axis and extending out towards the right-hand side. So remember, when you talk about an inverse function, you're talking about a function that undoes another function. So let's say that we have, for example, a function like 2x minus 4, and we want to find the inverse function to it. We take y equal to 2x minus 4, and then to find the inverse, we label it inverse, and then we swap the x and the y variables. Hopefully this is review for you from algebra. So once we swap the variables, then we solve for y again by moving the 4 to the other side. So we get 2y equals x plus 4, and then we divide everything by 2 so that we have x plus 4 divided by 2. And this becomes the inverse function to the original function, which was 2x minus 4. And they actually do the order of operations in completely the opposite order. So for example, if you're looking at the original 2x minus 4, it multiplies by 2 and then subtracts 4. So think of that in your head, kind of fix that order. Multiply by 2 first, then subtract 4. So to undo it, you add 4 first, and then divide by 2. So they're inverse functions in that they completely undo one another and they reverse the order of operations. Now, inverse functions make mirror images of themselves across the identity function. So when you're looking at this graph, the identity function, again, is the graph y equal x. And that's because when you swap the x and y, you get the same graph again, y equal x, x equal y. It's the same equation. It doesn't change form like this one did. Also, because it is its own inverse, when you fold it on itself, it is itself, right? And when you swap the ordered pairs on the graph, so for example, if we swapped this ordered pair here, 9, 9, when you swap the x and the y coordinates, you still have 9, 9. So the identity function is the only function that is its own inverse 3 ways, algebraically, graphically, and point to point. So there are other functions that are their own inverse algebraically. The inverse function 1 over x is an example, y equal 1 over x. If you swap the x and y, you'll again get y equal 1 over x. But when you swap the ordered pairs, you do not get the same point. So for example, 2 comma 1/2 would become 1/2 2. So it is its own inverse algebraically and graphically, but it is not its own inverse point to point. The only function that's its own inverse point to point and algebraically and graphically is the identity function, which is why it has a name. So these two graphs make a mirror image of each other. If we fold the graph along the identity function, if we make this the crease of the paper, then these two parts fold together and touch. All right. So the next thing that we're talking about is looking at the slopes of these two lines, because remember, the slope of the tangent line is in fact the derivative. So since we have slope of the tangent line, we want to compare the slopes of the tangent lines on these two graphs. So if you're looking at the original function up here, you can see that the slope of the tangent line would be rise over run, and that would give us Q over P. So it's written up here, the slope of the tangent line on the original function is Q over P. All right. Now, notice that they've got this F prime of F inverse of A. Where did that come from? Well, if we take this point down here, which is on the inverse function, and I'm talking about this point right here, I'll put an X on it. If we call this one A, then the Y value becomes F inverse of A using the inverse function notation. So this is A, F inverse of A. But remember that inverse functions also invert points. So they invert the coordinate values on points. So the point that corresponds to A, F inverse of A is F inverse of A, A. So these 2 points actually would touch when you fold it together along the identity function. They're the ones that come together and touch. So we swap the ordered pairs to get us this, so that this value right over here on the x-axis is actually F inverse of A. All right. So that's the value on the x-axis. So what this is saying is the slope of the tangent line at that point is Q over P. So the slope of the tangent line at F inverse of A is Q divided by P. Now, what we're interested in is not the slope on the original function, but the slope on the inverse function. So we want to come down here and compare what's happening on the inverse function and see what's going on. So when we look at this one, because it inverts the x and the y coordinates, the slope on the inverse function, which is F inverse prime at A, which this is A right here, and I need to label that. There's A. This becomes P over Q. So the slopes on their tangent lines, because we're swapping x and y coordinates, become actually reciprocals of one another. So the slope on the inverse function is P over Q. So the question is, how can we use this information to come up with a formula? We're looking for this right here. This is our goal right here. And what we know is the slope on the original function. So all I need to do to get this P over Q is take the original derivative on the original function and take its reciprocal. So this is also equal to 1 over Q over P. Does everybody buy that? All right. When I take 1 over the reciprocal, then that is going to give me P over Q. But I can also write that then using the formula. This is 1 over F prime of F inverse at A. This is the formula for the derivative of an inverse function. This is the formula right here. 1 over the derivative of the original function and substitute in place of x the inverse function value at A. All right. So this is our formula, and we'll see it on the next page. We're looking at it right here. Here's the formula. To find the derivative on the inverse graph, we take the derivative on the original function and plug the inverse function inside of it. Now, in order to do that, that means that we have to know the original function and we have to know the inverse function. And this is why we don't use this formula very often, because we don't often know both of those pieces of information. And finding the inverse function from the function is a lot of work. You have to swap the x and y variables, and then you have to solve for y again. That would be all this work that we did here on the left. This is the process of finding the inverse function. So it's not a trivial formula to use. It's something that requires quite a bit of work to do. So again, we primarily use this in order to find the derivative of inverse trig functions. So now what we're looking at here is again the formula. This is just the derivative of the inverse function is 1 over the derivative of the original function with the inverse plugged in. Now, if we let the inverse function be g of x, then we can say g prime of x is 1 over f prime times g of, or not times, but with composed with g of x. So let's see how to apply this theorem together. We're going to apply it on this function right here. We have the function g of x equal to 1 over x plus 2, the quantity. All right, so we have this function to look at. This is an actual inverse function. It's called an inverse function because of the way that it is done. It's been shifted to the left 2. So it's been shifted over here. X cannot be negative 2. So this has the basic graph that looks something like this. All right, so that's what our graph looks like right there. That's the basic graph of 1 over x plus 2. So one of the things that we need to know is we need to find the inverse function. We have to know what function g is the inverse of. We want to find the derivative of it. All right, so the derivative of g of x. So the first thing we're going to do is apply our college algebra skills. We're going to swap the x and y variables, and we're going to solve for y again. So this is the same thing I did in the original problem, looking for the inverse function, right? So the first thing we do is we replace g of x with y, and then we swap the x and y variables to find the inverse function to it. So y becomes x and x becomes y. Then we're going to solve this equation, x equal 1 over y plus 2. We're going to solve that for the y variable again. So when we solve it for the y variable again, we move the y plus 2 to the left. And so this becomes 1 equals x times quantity y plus 2. Now we're trying to solve it for y and isolate y. So the easiest thing to do next is simply to divide both sides by x. And so we solve for the y plus 2 factor, which gives us y plus 2 equals 1 over x. Then we subtract the 2 and we get y equal 1 over x minus 2. So this becomes our function, 1 over x minus 2. So this is the function for which the original was the inverse. All right, so the original is the inverse and this is our function. All right, so now we're going to apply the formula. So we have f of x is equal to 1 over x minus 2, and f inverse of x, which is equal to g of x, is equal to 1 over x plus 2. All right, these are the two functions we're working with. We want to find the derivative on this function. It is the inverse of this function. So this becomes our original function. And we're going to apply the formula to it. So the first thing we have to do is find the derivative of the original function. So the derivative of 1 over x minus 2, you can use the quotient rule, or you can take this f of x equal to 1 over x minus 2 and write it as x to the negative 1 minus 2. And then when you take the derivative of it, you get negative x to the negative 2 plus 0, since the derivative of negative 2 is 0. And then you can take this, it's got a negative exponent, so you can drop it again to the denominator, and that will lead to this formula right here, negative 1 over x squared. All right. This is another one that you see quite a bit. I'm not going to require that you memorize it, but it may be one that you do want to memorize because the derivative of 1 over x shows up a lot, especially in calculus 2. It's sort of ubiquitous. It's just everywhere. Okay, now it's time to apply the formula. So we have the derivative of the original function, and we need to replace it, the x variable inside the derivative, with the inverse function, which is 1 over x plus 2. So we have -1 over something squared, and the something becomes 1 over x plus 2. All right. So we're just applying the formula. This is f inverse of, f prime of f inverse at x. All right. So we have f prime of f inverse at x. So we took the derivative of the original function and we substituted the inverse function inside of it, which gives us this. Now, this is not the formula. Remember, the formula for it has that in the denominator. So we're going to need to take that and simplify it, and then we'll take the reciprocal of it, 1 over that, and that will give us the formula for the derivative on the inverse function. All right, so that's what we do. We take the derivative of the original with the inverse function substituted inside, which is here, and we place it in the denominator for the formula. And remember that the bottom of the bottom is the top. So when you're dividing by a complex fraction, the denominator of the denominator flips to the numerator. So this becomes on top. We still have a negative on it. And of course, 1 squared is still 1. So this becomes -1 over x plus 2 quantity squared. So this means that the derivative with respect to x of the formula, what was the original again? I've got to go back and find it. 1 over x plus 2 is -1 over x plus 2 quantity squared. All right. Now you may ask yourself, is that shorter than just finding the derivative directly? And the answer is going to be no. It is not shorter. In fact, it's longer. All right. So remember, I said we don't actually typically use this formula to find the derivative. I would find this more easily just by applying the quotient rule to the inverse function. Where do we use this formula then? We use it to derive the inverse trig formula's derivatives. So arcsine, arctangent, arccosine, we need this formula to find their derivatives. Okay. Now, let's take a look at example 2. So we'll practice it one more time, and then we'll go ahead and take a look at the inverse trig ones. Okay. So we're looking at the derivative of g of x equal to the 5th root of x, and we want to find the derivative by applying the formula to it. Okay. So we're going to say that g of x equal to the 5th root of x is equal to f inverse of x for some function f. Now we need to find f. We need to find the original. What is that the inverse function for? So we need to find the original function by swapping the x and the y coordinates. So the first thing we're going to do is we're going to take the g of x and replace it with y. And this gives us y equals the 5th root of x. So we're just replace the notation with y. All right. The next thing we do is we swap the variables to get the x and the y. So we get x equals the 5th root of y. So we swap x and y for the inverse. And this is going to give us the original function. And now we need to solve for y. So we're going to have to raise both sides to the 5th power. Now, raising to the 5th power is not risky because the power is odd. If it were an even, it would be more risky because we would lose information about whether it was positive or negative. But when it's odd, we don't have to worry about that. So now we are simply going to solve for y. So this gives us y equals x to the fifth. So this is our new function, the original function, x to the fifth. So we have the function f of x equals x to the fifth. So g of x, which is f inverse of x, is equal to the fifth root of x. All right, these are our two formulas right there. All right. Now to apply the formula, we have 1 over, oops, hang on just a second. Thought I was here. Okay. So our formula for g prime of x, which is f inverse of x, the derivative of it, is equal to 1 over f prime of f inverse of x, which is 1 over f prime of g of x. Right? So I need the derivative of the original function f. So the derivative of x to the fifth, f prime, is going to be 5x to the fourth. So I'm going to come down here and I'm going to write 5 times something to the fourth. And this is all in the denominator of the fraction. So I have 5 times something to the fourth. And then I'm going to substitute in here whatever the inverse function was, which in this case is the fifth root of x. So this leads us to write, and this comes from college algebra. So if you're a little shaky on your rules, this is a good review. Remember, the fifth root is the 1/5 power, and it's also raised to the 4th power. So this gives us the 4/5 power. So this is 1 over 5 x to the 4/5. Right? And that's the formula. Now, again, this is not doing this as a shorter method. It would be shorter to find the derivative directly. We're simply practicing the formula because what we're going to do is we're going to use it to find the derivative of the inverse trig functions, arcsine, arc cosine, etc. It's really the only way to find those. We're going to skip example 3. It's longer. So we're going to skip that one today. And we're going to go on to using the inverse function theorem. There are 2 cases where it comes in handy. The power rule for rational exponents, which I've already given you. So you already have it, but the proof of it is right here. We're not going to go through the proof, but I include it for completeness in the notes. But basically, this just says if you have a fractional exponent, you can bring it to the front and subtract 1 from the fractional exponent. And the way to prove this formula is to use the inverse formula for derivatives. All right. And now we're going to take a look at the derivatives of the inverse trig functions. These are a little bit weird. In fact, they're going to be the first time that we've taken the derivative of a type of function and gotten a different type function. So in the past, if we had something algebraic, like a polynomial x squared plus 2x plus 3, and we took the derivative, we got 2x, what did I say, x squared plus 2x plus 3, we got 2x plus 2, which is still algebraic, right? It's still a polynomial. So we took the derivative of a polynomial and we got a polynomial, so that the derivative of the algebraic function was still algebraic. When we take the derivative of e to the x, we get e to the x. So the derivative of an exponential is an exponential. When we take the derivative of a trig function like sine, we get cosine, which is still a trig function. So we're maintaining the type of function when we take the derivative. Now we're going to see something truly unusual and different. The derivative of the inverse trig functions is not an inverse trig function. It's algebraic, which is wild. I remember the first time I studied this, it took me a long time to wrap my head around how the derivative of an inverse trig function could end up being some kind of algebra expression. So this is what's going to happen. We're going to start with arcsine, and we're going to derive the formula for the derivative of arcsine. So again, what we're trying to find is this right here. We're trying to find the derivative with respect to x of the arcsine of x. This is what we're trying to find. So we're going to apply the formula, and the formula is 1 over the derivative of the original function, for which this is the inverse, with the inverse function plugged inside of it. Now, we know that the functions sine of x and arcsine of x, these are the one-to-one inverse functions of each other. They undo each other, right? You feed sine of x an angle, and it gives you back a value. If you feed arcsine the value, it will give you back the angle. So they've swapped the x and y variables. So sine of x and arcsine of x are inverse functions. So our original function here, f of x, is sine of x. And our inverse function, f inverse of x, or you can call it g of x, is equal to arcsine of x. These are one-to-one inverses of each other, at least over the interval from negative pi over 2 to pi over 2. Remember, we had to restrict the interval really small in order to get it to be a one-to-one piece. So they have these really, really limited domains, all right? Okay, so we apply the formula, which says take the derivative of the original function, which is sine, and the derivative of sine is cosine. And then in place of the variable x, substitute the inverse function arcsine of x. So hopefully this makes sense to you how we're using the formula to derive the derivative of arcsine of x, which is 1 over cosine of arcsine. Now, I promised you that this was going to be a really weird result and not be related to trig at all. So we're not done, all right? This is not the end of it. This is only part way through the formula. What we have to do now is we need to draw a triangle. We need to draw the triangle for which the sine of x is, or the angle for which the sine is x, all right? So we're going to draw a triangle, which will be the next thing we do. And we're looking for one where the angle whose sine is x. So here's our angle in the lower left-hand corner, and the sine of this angle is x. That means the opposite side is x and the hypotenuse side is 1. That means that we knew the opposite and we knew hypotenuse. We did not know the adjacent side. How did I derive the adjacent side? What did I use to get the adjacent side?
Pythagorean,
Yep.
like a squared equals b squared plus c.
Yeah, a squared plus b squared equals c squared, the Pythagorean theorem. So I applied that. This 1 is on the hypotenuse, which is c. So this became c squared minus b squared, which is 1 minus x squared under a radical to give us the actual value of it. And it is a length, so it's got to be strictly positive. So I knew the opposite side, I knew the hypotenuse, and I used the Pythagorean theorem to find the missing side. Now, what we're looking for is something that says the cosine of that angle is something. So I have 1 over cosine of arcsine of x. So this is what I'm trying to find. 1 over cosine of the arcsine of x. Now remember, arcsine of x represents an angle. So this is really 1 over the cosine of some angle theta. Arcsine is the angle itself. That's what arcsine represents. So this is 1 over the cosine of some angle. What angle? That angle right there in the lower left-hand corner. So it's actually referring to the cosine on this triangle. And the cosine on this triangle is going to be the adjacent side divided by the hypotenuse. So since this is in the denominator, I get 1 over the square root of 1 minus x squared over 1, which reduces to 1 over the square root of 1 minus x squared. This is the derivative of arcsine. It has nothing to do with trig. It doesn't have anything to do with inverse trig functions. It is, in fact, algebraic. It's not a rational function because of the radical, but it is an expression involving algebra only, adding, subtracting, multiplying, dividing, raising the powers, and taking roots. That's algebra, all right? So the derivative of arcsine is 1 over the square root of 1 minus x squared. Really strange, all right? Now we're going to repeat the process and we're going to find the derivation of arc cosine of x. So our original function here is cosine, and our inverse function, this is f inverse of x, is equal to arc cosine. And remember, you can either use the inverse function notation or you can use the arc notation. I prefer the arc notation because I think it avoids that careless mistake of thinking it means power. It's not a power, it's an inverse function, all right? It undoes the cosine. So we apply the formula, take the derivative of the original function that it is the inverse for. So the derivative of cosine is negative sine. So we have negative sine of something. And then the something becomes arc cosine of x. So this becomes negative sine of arc cosine of x in the denominator for the formula. Now the next thing we're going to do is we're going to draw a triangle. We want to draw the triangle for which the arc cosine is x. What angle has a cosine that's x? So we draw a triangle. We want the cosine of it to be x. So the adjacent side is x and the hypotenuse is 1. That means we don't know the opposite side, but we can use the Pythagorean theorem to find it. And then once we use the Pythagorean theorem, we had this. Now I want to come back to this formula because this is basically saying 1 over negative sine of that angle, because arc cosine of x represents that angle in that triangle right there. So we need the sine of this angle, which is going to be the radical over 1, which becomes just the radical. So this is going to become 1 over negative the square root of 1 minus x squared. So it's the same as the derivative of arcsine, but it has a negative. Remember how the derivative of all of the co-functions for trig had negatives on them? All the derivatives for the co-functions of the arc functions are also going to have negatives on them. So the derivative of arc cosine will be negative. The derivative of arc cosecant will be negative. And the derivative of arc cotangent will be negative. But the derivatives of the primary three, arctangent, arcsine, and arcsecant will be positive. Okay, now we're going to derive the formula for arctangent. This one I haven't worked out for you, so we're going to do it ourselves. So we're going to think about where we have an inverse function. So on the interval from pi over 2 to pi over 2 open, remember we can't allow it to be pi over 2 because cosine is 0 there. Tangent and arctangent are inverse functions of each other. And they're 1 to 1. Right? So these are our two functions that we have right here. So we're going to write our original function is going to be tangent of x. And the one we're trying to find the derivative of is f inverse of x, which we can call g of x just to make the notation easier, is arctangent of x. All right, that's the one we're looking for. So we're going to apply the formula. And the formula says that the derivative with respect to x of the arctangent of x, which we can also use the inverse function notation, tan inverse of x, is equal to 1 over f prime of f inverse of x, which is 1 over f prime of g of x. So this is the formula that we want to apply. All right. And again, this is the one time when it is more helpful to use the formula because it allows us to derive the expression for it. Normally, this is not the way that we would find the derivative of an inverse. We would just do it directly. But for inverse trig functions, this is really the only way to go. So now we need to find the derivative of tangent. What is the derivative of tangent? Who remembers? What's the derivative of tangent?
I think is secant squared.
It is secant squared.
Okay.
So we have secant squared of something, and the something is going to become our inverse function, which is arctangent of x. So we have secant squared of arctangent of x, or tan inverse of x. All right. Now we're going to rewrite this in a couple of different ways so that we can apply the formula and find a triangle to work with it. So one of the things that we're going to do next, and I'm going to need a whole lot more space than I left myself here to do this problem, is we're going to rewrite the second power on the outside of everything. This really means that I have the secant of arctangent of x, and the whole thing is being squared. That's really what that square means, that it's on the outside. Now, what is arctangent of x? Arctangent of x, remember, is some angle theta. So this actually represents over here somewhere some angle theta. So I've got the secant of some angle theta, and that whole thing is being squared. So now I want to draw my triangle. All right. And I need the angle whose tangent is x. All right. I need the angle whose tangent is x. That is arctangent of x. So what angle? So this is going to be my angle. Oops. I don't know how that happened. This is going to be my angle theta down there in the lower left-hand corner. And I need the one for which the tangent is x. Now, tangent is opposite over adjacent. So I can think of this as x divided by 1. So I need the opposite side to be x and the adjacent side to be 1. And then I can apply the Pythagorean theorem, and that will give me my missing side. So when I look for the missing side, this is going to have to be the square root of x squared plus 1. All right, so that's my missing side, the square root of x squared plus 1. Everybody follow how I got the triangle and I got the hypotenuse? All right. Let's go back then and let's substitute this into our formula over here. The formula says I want the secant of that angle. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So this right here is hypotenuse over adjacent. So when I look at the hypotenuse, I have the square root of x squared plus 1 divided by the adjacent, which is 1. Remember, adjacent is touching or attached to the angle theta. So this gives me the square root of x squared plus 1, and that's going to replace the secant of theta. So this becomes 1 over, in brackets, the square root of x squared plus 1 squared, which is going to give me 1 over x squared plus 1. This is the derivative of arctangent of x. Right? This is actually a rational function. It does not have a radical, so it is a rational function. It's the ratio of two polynomials, the constant function 1 and the polynomial x squared plus 1. So it is a rational function. Okay, that gives us arctangent of x. Let's now take a look at the derivation of arcsecant of x. Arcsecant of x is a little bit more complicated. It's a little bit trickier than the others because arcsecant of x has a domain that is split apart, and this causes us a little bit of a problem. It goes from including 0 to pi over 2, but not including pi over 2. And it looks like I've got my slash backwards. I don't know how that happened. And then pi over 2 to pi. That's okay. I'm not sure how I did that. How did I get a backward slash instead of a forward slash? All right, they're not even close to each other on the keyboard. Okay, so we've got the functions f of x is equal to secant of x, and the inverse function is arcsecant of x, or the inverse secant function. They're one-to-one functions of each other. But because this is 1 over cosine, we have to eliminate pi over 2 from being in our domain. We can't allow pi over 2 to be in there. Now we're going to use the formula that we've been using today, 1 over the derivative of the original with the inverse function substituted inside. Now the derivative of secant is secant tangent. So we have two places to substitute the inverse function. We have secant of something, tangent of something, and we substitute arcsecant of x into both of those places. So now we have 1 over the secant of arcsecant and times the tangent of arcsecant. Okay. Now we need to draw a triangle in order to find the rest of it. When we draw our triangle, we're looking for something to represent the arcsecant of x. So this is what this triangle is to represent. So the secant of this angle is x. The secant of theta is x. And secant is hypotenuse over adjacent is equal to x over 1. So that tells us the hypotenuse is x and the adjacent is 1. So this is your trigonometry coming into play here. This means that the opposite side is unknown. Then we use the Pythagorean theorem. We square the hypotenuse, subtract the square of the adjacent side, which is still 1. And that gives us the square root of x squared minus 1. Since it is a length, it has to be strictly positive. All right. Now we need to substitute into the formula the secant of that angle and the tangent of that angle. So again, this is actually representing 1 over the secant of that angle times the tangent of that angle. So we need to represent the secant of that angle and the tangent of that angle, since arcsecant of x represents an angle. So the secant is going to be x over 1. Does everybody see that? That's the secant. Hypotenuse over adjacent. Tangent is opposite over adjacent. So it's going to be the square root of x squared minus 1. All right. So this is going to give us 1 over x times the square root of x squared minus 1. Now, this works in quadrant 1 where everything is positive, because if we're in quadrant 1, then we know that they've got to have the same signs. It's positive in quadrant 1, but it would be negative in quadrant 2. So we've got a little bit of a problem here in that when we write the radical notation always represents a positive value unless you have a negative sign on the front. And the x in quadrant 1 would also be positive. So this expression can only represent a positive value as written. Now, the problem is if we're in quadrant 2, things change. If we're in quadrant 2, we know that the secant should be negative, but the tangent should also be negative. Now, secant is negative in quadrant 2 because it's the reciprocal of cosine, and cosine is x. In quadrant 2, x is negative. So the secant should be negative in quadrant 2. But the tangent is also negative in quadrant 2 because tangent is y over x, and y is positive and x is negative. That's a problem because if they're both negative, it should turn up positive. And if I use this formula, it won't. If I use this formula, the x would be negative because I'm in quadrant 2, but the radical would represent a positive value. So this would be negative. And I need it to turn out to be positive because I'm multiplying secant times tangent. So what we do instead is we throw in a negative to force it to become strictly positive. The x value itself is negative, and that negative will make it a positive. So this is giving us this formula right here. Now we can use, this is a problem for us because this is the formula in quadrant 2. And the formula for quadrant 1 is this one. And they're opposites. Formula for quadrant 1. All right, they're opposites. So what we do, because it is split by the quadrants 1 and 2, is we use the definition of absolute value that when x is positive, it's positive, and when x is negative, we do the negative of x to replace this x, negative x, in the 2 separate formulas and to write it as one combined formula with an absolute value. All right, so we have 1 over the absolute value of x times the square root of x squared minus 1. This is the formula for the derivative of arcsecant. This will guarantee that the full value turns out to be positive no matter what. Because again, in the denominator, we had a secant times a tangent, and both the secant and the tangent are negative in quadrant 2, which should force the entire thing to be positive. And by putting the absolute value around the x and knowing that square roots by themselves are strictly positive, this will guarantee that it's positive in both quadrants 1 and 2. All right. So let's take a look at the formulas for the inverse trig derivatives. This is the preferred U form with the chain rule built into it. So the du dx represents the derivative of the inside function. So du dx is the derivative of whatever the inside function is. So the derivative of arcsine is 1 over radical 1 minus u squared du dx. Now it does carry restrictions because of the radical. We don't want a negative under the radical. So u has to be between -1 and 1. Notice that the derivative of arc cosine is -1 over 1 minus u squared. It's the identical function to arcsine, but with a negative on it. It also carries the restriction that u has to be between -1 and 1. Otherwise, we get a negative under the radical, which would make it imaginary and not real. All right. Not meaning exist, not exist, but different types of numbers. Then we have arctangent, which we found was a rational function, 1 over 1 plus u squared times du dx, the derivative of the inside function. There's no restriction on the u here. U can be anything from -infinity to infinity. there's no way when you square the u that it can end up being a -1. That's the only thing that might cause a problem. But when you square it, it becomes strictly positive or at minimum 0. So you don't have to worry about that. We didn't derive arc cotangent, but we could have. And it would have given us the same formula as arctangent, but with a negative on the front. All right. And again, no restrictions on u. Looking at arcsecant and its inverse arc or reciprocal function arc cosecant, we have 1 over the absolute value of u times the square root of u squared minus 1 du dx. We have to make, excuse me, we have to make sure that u is greater than 1, or when we square it, it will get smaller, and then we'll have a negative under that radical. So notice that these are identical formulas as well. The only difference is the arc cosecant has a negative on it, right? So these are all of our formulas for the derivatives of the inverse trig functions. And now we just want to practice it. Okay. So in practicing, what we want to take a look at first is the arc cosine of 3x minus 1. This is our first formula to look at. All right. So we're looking at this one, and I'm going to write down the formula for arcsine, or arc cosine rather. The formula for arc cosine, which you may have already forgotten. Of u is equal to -1 over the square root of 1 minus u squared du dx. All right. So what is u? U is the thing that's been substituted inside of the arc function. So our u is 3x minus 1. All right. So the first thing we're going to do to take the derivative of the inverse cosine of 3x minus 1 is we're going to take a -1 and divide by the square root of 1 minus u squared. U is going to be our 3x minus 1, so we square that. And then we multiply this by the derivative with respect to x of the 3x minus 1. All right, that's what we mean by the derivative of the inside du dx. Okay, taking a look at the next one. What have we got for the next one? For the next step, we should finish it. The derivative of 3x minus 1 is 3. So this gives us a -3 over the square root of 1 minus 3x minus 1 squared. Now you can multiply that out in the denominator if you want to, but I'm not going to require it. I think it's okay to leave it in the form that you've got right now. Let's take a look at example 6. Find the equation of the line tangent to the graph arcsine of x at x equals 0. Remember, we need two things. We need the slope of the tangent line at 0, and we need the point at 0. So let's get our point first. First, to get the point, we know that x is 0, and we need to find the y value. So f of 0, which is arcsine of 0, is saying the angle whose sine is 0 is what? Well, what angle gives you a sine of 0? 0 does, 0 radians. So this is going to give us 0. So this is going to be the point 0, 0. Right? Now we need the slope of the tangent line. So to find the slope of the tangent line, we find the derivative. So now we can find f prime of x, which is going to be the derivative with respect to x of the inverse sine function, arcsine, which is 1 over the square root of 1 minus something squared times the derivative of the something. All right, now what is inside of it? Well, the only thing inside of it was x, and the derivative of x is 1. So this is going to give us 1 over 1 minus x squared under the radical. All right. Now to find the derivative at 0, what we need to do is to replace the x with 0 so we can find the slope of the tangent line at x equals 0. And this will give us f prime of 0, which is 1 over the square root of 1 minus 0 squared, which is 1 over the square root of 1, which is 1. So when we plug it into our formula, remember that our formula for point slope has the point coordinates next to the variables x and y and the slope of the tangent line outside the parentheses. So ours becomes y minus 0, this is y1, this is x1, equal to 1 times x minus 0, which reduces to the equation y equal to x. Now, what does that mean? So if we look over here onto Desmos, and we're going to reset the graph. All right, so I've got the graph here, and let's reset the graph. So let's do arcsine of x. I'm not sure if it takes arcsine or not, but I think it does. Yeah, it does. So there's arcsine of x, y equal arcsine of x. And now let's graph y equals 0, or y equal x rather, at the origin, 0, 0. All right, and let's blow it up a little bit so we can look at it. Put the label on there. So what we're saying is at that point, 0, 0, the tangent line to the graph is that line y equal x, and it is tangent to the inverse trig function at that point. Right? Now let's find the derivative for the formula arcsecant of 1 over x. And remember that you can also write this as arcsecant, and you can write 1 over x as x to the negative 1, which may help when we do the derivative of it. So our formula for this one for arcsecant is derivative with respect to x of the arcsecant of u is equal to 1 over the absolute value of u times the square root of u squared minus 1 times the derivative of the inside function du dx. And that, of course, is the chain rule built in. Okay, so to apply the formula, we're going to find dy dx, which is going to be equal to 1 over the absolute value of whatever is inside the arcsecant function, which is 1 over x. So our u is 1 over x. So u becomes 1 over x. We're simply applying the pattern that we see here. And then we multiply by the square root. Now we take that and we square it. So 1 over x squared. And then we subtract 1. And then we multiply by the derivative with respect to x. And this time I'm going to write it as x to the negative 1. All right. Since it's easier to take the derivative in the power form, then I rewrite it in the power form. Then this represents the same thing as 1 over x. Now I can simplify this a little bit, this gives me the absolute value, 1 over the absolute value of 1 over x times the square root of 1 over x squared minus 1. And the derivative of x to the negative 1 is a negative 1 x to the negative 2. All right. Which gives me a negative 1 over x squared. And remember, I said this is one that shows up quite a bit and might be worth memorizing at some point. So I have 1 over the absolute value of 1 over x times the square root of 1 over x squared minus 1 times negative 1 over x squared. The negative 1 can go into the numerator and the x squared can go into the denominator. And this leaves us with negative 1 over x squared times the absolute value of 1 over x times the square root of 1 over x squared minus 1. Now, there is more algebra that you could do here. You could pull the x squared either into the radical, or you could pull it into the absolute value, because x squared is strictly positive, and you could do a little bit of reduction here. It won't remove the absolute values. Instead, it will just keep it inside the absolute values, but that is something you could do. So you could rewrite this one as negative 1 over the absolute value of x, since x squared divided by x reduces. And this would give you 1 over x squared minus 1. All right, so that's another way to write the solution. Now let's look at a composed function that's got this together. Okay, when we're looking at this function, it's a composition of functions. We have a radical on the outside as the last thing done, the most outermost function. And on the inside, we have cosecant. And inside cosecant, we have x. So remember, for this, we take the chain rule and we apply derivative of the outside function, freeze the inside, times the derivative of the inside. So to do this one, to find dy dx, we're going to take the derivative of the radical, which I told you to memorize, is 1 over 2 the radical times the derivative of what was on the inside, which was the inverse cosecant of x. So 1 over 2 the radical, the inside is frozen, at still inverse cosecant of x. Now, the derivative of inverse cosecant is 1 over the absolute value of u times the square root of u squared minus 1, with a negative 1 in the numerator. Because it's a cofunction, it has a negative radical. So this becomes 1 over 2, the square root of inverse cosecant, times negative 1 over the absolute value of the inside function x, times the square root of the inside function squared minus 1, times the derivative of the inside function, which is x. Now, the derivative of x is just 1, so it's not going to change anything, but that is the chain rule in action right there. So then we can combine everything sort of together, although honestly, I probably would not combine those two radicals because they're totally different types of functions. I would probably leave it like this. I would probably put the absolute value in front, and then the square root of x squared minus 1. So I would probably write it like that as the final result. Okay, are there any questions about what we're doing so far?
Memorizing a lot of things.
Yeah, There's a lot to memorize. However, and I'm glad you brought that up, Caleb. Not all mathematicians agree, but I do not expect my students to memorize the inverse trig functions. If you need the derivative of the arc secant, arc cosine, arc sine, I will give it to you on the exam. So you do not need to memorize those particular ones. Some instructors require it. I do not. I feel like they're so complicated that it's very easy to get them confused, and you have enough to memorize already. I think it's better to go look it up when you need them, right? So you will not need to memorize them for me. Okay, one last example, and we're going to get on to the next thing. This is about a moving hockey puck. And the position of the moving hockey puck after t seconds is arctangent of x, where s is in meters. All right, so s is the position of the hockey puck. All right, so we have arctangent. So we want to find the velocity of the hockey puck at any time. Velocity is the derivative of position, so we'll need to find the derivative of arctangent. And then we want to find the acceleration of the puck at any time. So then after we do that, we'll have to find the derivative of the derivative, because acceleration is the second derivative of position. And then we're going to evaluate it at 2, 4, and 6 seconds. And then we're going to see whether we can determine if it's speeding up or slowing down. Okay, so the first thing we want to do is we want to take our formula for the position, which is s of t equals arctangent of t. And we want to find the velocity. So the velocity of this, v of t, is equal to s prime of t. And remember, our formula for arctangent is 1 over u squared plus 1 du dx. So this becomes 1 over t squared plus 1 times the derivative with respect to t of t. Notice that the formula has changed to d by dt, not d by dx. Because the independent variable is t, this becomes a dt in the bottom. We call this the differential, all right? So the differential changes depending on the independent variable. Ours is t, so it's d by dt, not d by dx, all right? So once we have that, the formula that we're going to get from that is going to be 1 over t squared plus 1. Now we can also write this in parentheses as t squared plus 1 all raised to the -1 power. And why I did that is I'm preparing myself to do the derivative again, which would give me the acceleration. So the second derivative of position is acceleration, which is part B. So a of t is the first derivative of velocity and the second derivative of position. So now I apply it to the power form. And when I apply it to the power form, the -1 comes to the front, reduce the power by 1, take the derivative of the inside function. So derivative of the outside is a -1 raised to the -2 times the derivative with respect to t of what was inside t squared plus 1. We freeze the original inside at t squared plus 1. And when I take the derivative of t squared plus 1, I get 2t. So I have -1 times t squared plus 1 to the -2 times 2t. Now the -2 could drop to the denominator because it has a negative exponent, but the -1 and the 2t will stay put in the numerator. T squared plus 1 quantity squared. Okay. So these are my two formulas for the velocity and for the acceleration. And in part C, we want to find these at 2, 4, and 6 seconds. So we can find V of t and A of t, and 2, 4, and 6. So we'll create a small table here of values, right? So at 2 seconds. When I plug in 2 into the velocity, 2 squared is 4 plus 1 is 5. So I get 1/5. When I plug 2 into the acceleration function, I get a -4 in the numerator and 5 squared in the denominator, which gives me 25. So I have -4/25. Okay. When I plug in 4 for the velocity, I get 16 plus 1 is 17. So I have 1/17. And when I plug it into the acceleration, I get -8 over 17 squared, which is 289. So I get -8 over 289. Okay. Then when I plug in 6 to the velocity, I get 6 squared is 36 plus 1 is 37. So I get 1/37 for the velocity, which is small, right? So it's not moving very fast. In fact, it's barely moving at all. And then when I plug it into the acceleration, I've got a -12 over 37 squared, which turns out to be -12 over 1,369. Okay, so here's my V of t and my A of t. And we want to decide, is it speeding up, slowing down? What's it doing? Well, notice that the velocity is always positive and the acceleration is always negative. So they always have opposite signs. So because it has opposite signs, this means that it's slowing down at all points in time. At 2, 4, and 6 seconds.